Okay, so let's carry on from where I left off yesterday. And just want to recap, we're talking about computing e to the a times a vector. And I mentioned that one of the 19 dubious ways of Moeller and Van Loon is this one here, where they apply a 4-stage Runge-Kutta method. So they've got a degree 4 Taylor polynomial, and they're essentially splitting the range of integration into m pieces and using this degree 4 polynomial m times, applying that to the starting vector m times. So there's no mention here of accuracy. You'll just get whatever accuracy that degree 4 polynomial happens to give you, and we don't a priori know what that is. So I'm going to describe an algorithm that actually is along the same lines. It uses this same idea of splitting the range of integration. But just before I go into that, just let me say what the assumptions are here, because it's very important to be clear what assumptions you're making when deriving an algorithm. So what am I assuming? I assume that I can compute AX. So I've got a little box that if you put X in, you get AX out. So I can do matrix vector products. I also, for this algorithm, will need the ability to do A star times X, or A transpose times X, because I'm going to estimate some matrix norm, some vector norms, and I will need the transpose for that. If I didn't have the transpose, I can still go ahead, but I won't get quite as good estimates. So that's what I'm assuming is given, and then what the algorithm should do. So the algorithm is just a black box. You give it a tolerance, you give it an A and a B, and it should give you out, or back, e to the AB with error toll, error bounded by toll. And I'm not yet being precise about what I mean by error. Okay. So that is the setup, and I want you to be giving me, I'm not going to put any restrictions on toll. So toll could be 10 to the minus 1, 10 to the minus 5, 10 to the minus 16, anything within reason. Okay. So that is the problem I'm aiming to solve with this algorithm. It doesn't require any more assumptions about A. It doesn't need to know the largest eigenvalue of A, the smallest eigenvalue, anything else about A. Okay. And clearly, if you throw more information in, if you tell me that A is symmetric and you have an estimate of the largest and smallest eigenvalues, I might want to do something different. Okay. But the algorithm is really defined for this very general setting, so it can be used as a black box. And rather than just e to the a times a vector, let's handle e to the a times several vectors. So the matrix B has got n0 columns. But I want B to be tall and thin. So n0, n0 is much less than n. N0 is 1 is certainly an important case. So what I'm going to do is write my e to the AB as, just as the 6 dubious way did. I'll split e to the a into s pieces of e to the a over s. And then I'll approximate each piece by a truncated Taylor series. So if I take m is 4, then that would become what was on the previous slide as the 6th dubious way. But I'll allow m to be any integer I like here. So I've now got two parameters in this method. I've got m, the degree of the polynomial, and s, which is the number of pieces I split the interval into. And I've got to come up with some way of choosing m and s. And I want to do that in such a way that I satisfy my error criterion and I use the minimum amount of work. So those are the two aims here. Okay. So how are we going to do that? How to choose S and M. So here's a little bit of analysis. Which is actually very simple. There's almost nothing to it. So at the top, I've said to myself, what I'm trying to do is approximate the exponential by a Taylor polynomial. So Tm of A is approximately e to the A. So it might make sense to look at e to the minus A times Tm of A. That should be close to the identity. And if I take the log of that and call it hm plus 1, then that should be close to 0, because the log of something close to I will be close to 0. Okay, so let me define hm plus 1 that way, and then just rearrange this equation. So if I exponentiate both sides of the equation, well, exp of log is just x, is just the argument. So exponentiating both sides, the left-hand side just gives me the argument of the log, and the right-hand side gives me e to the h plus m plus 1a. So that's just an immediate consequence. So that implies that. And if I multiply both sides by e to the a, I get this. And what I'd like to do now is put the right-hand side as e to the something, but I can only do that if the two matrices in question commute. So does A commute with h plus m plus 1a? Well, yes, it does, because hm plus 1a is a function of A. So it's a polynomial in A, it commutes with A. So I can write that as e to the A plus hm plus 1a, because everything's a polynomial in A. So that bit of analysis is entirely trivial. But what it tells me is actually not at all trivial. It tells me that the truncated Taylor series approximation is the exact exponential, not of A, but of A plus this perturbation. So this perturbation here is actually the backward error. Backward error is telling you how much you solved the problem within a certain distance of the problem you started with, and it tells you the size of that distance. So hm plus 1a is the backward error for this approximation. Now normally backward error is talked about in the context of rounding errors, and the backward error is normally entirely due to round off. Here the backward error is entirely due to truncation. So this is all exact arithmetic. There's no rounding error analysis yet. This is an exact arithmetic interpretation. Now the nice thing about backward error is that it's easy to decide how big you want it to be. So I can just now require that the norm of hm plus 1, I want this backward error to be bounded by tol times norm A. There's no condition number comes into this at all. It's simply, there's the original A, I don't want to perturb the original A by more than a relative amount tol. That would be the best possible result I could get. So this is much nicer than having to work out how big you want the forward error to be. This is the backward error. So that's going to be my aim. Choose S and M so that this inequality is true. So all the work is going to be in bounding hm plus 1. Okay. Now, at this point, I've ignored the fact that we are scaling A, but it's very easy to put the scaling back in here. If I just take this equality and divide A by 2 to the S, and then raise both sides to the power 2 to the S, well, not that one, do it here. No, 2 to the s there, and 2 to the s there. And then raise both sides to the 2 to the s. Just simplifying all that out gives you what's in the yellow box here. So the 2 to the s is straightforward to handle, and you get that the actual result of the algorithm is has this backward error, where I've got a 2 to the minus s there and a 2 to the s there. So this 2 to the s is really neither here nor there in terms of the what we can do with the analysis. So we want to select the degree, the scaling s, so that this is true. We also need to select m as well. So there's 2 things to select here. So we now know exactly what we're trying to do. And this idea, or this approach, this type of analysis, is actually in the original 19 Dubious Ways paper. And they were doing this for the Pardee approximant of degree 6. So everything I've said would work equally well with Tm replaced by any rational function. I haven't actually used the fact that Tm is a polynomial or that Tm is the Taylor series. So any rational function of A, that analysis still works. So they did it for the Pardee approximant. They forced n to be 6, and then they worked out that if they required the norm of 2 to the minus s A less than a half, then they could show that this bound was satisfied. Okay, but they artificially, well, they chose m is 6 and then chose s. So what I'd like to do is choose s and m together in some optimal way. And in my original paper on computing e to the a, what I did was I did a symbolic expansion of this series. You see, hm plus 1 is actually going to be a series starting with the power m plus 1. The reason for that is, I think, easy to see. Because e to the x, just do this for scalars, e to the x minus tm of x is a series that starts with, well, it's big O x to the m plus 1. So if I multiply through by e to the minus x, that will still be big O x to the m plus 1. And then if I take logs, or if I rearrange and take logs, then log of e to the minus x tm of x is log of 1 plus big O x to the m plus 1, which is big O x to the m plus 1. So that tells me that hm plus 1 will start, it will be a power series starting with terms a to the m plus 1. So in order to bound that tail of the series, what I can do is just symbolically work out the CKs and then use some high precision arithmetic to basically sum the series for a given norm A. So that's what I did in my paper, and that was what was different than what Moller and Van Loon did, in that you know, I'm going to some effort to compute this all symbolically, but I get a good sharp bound this way. And then I could, again in the case of rational functions, I could choose an optimal pair S and M. So here, though, we're dealing with the Taylor series, but we can use essentially the same idea. So basically what I'm going to doing is bounding that series by saying that the norm of this infinite series ck a to the k is bounded by the sum of the mod ck's by norm a to the k. Okay, k is m plus 1 to infinity. So that's what I'm going to use. Just take norms and use the triangle inequality in the obvious way. That's what I did in the 2005 work. But when we were looking at this again, myself and Awad Al-Mohi, who was my PhD student at the time, we realized that there's quite a lot of weakness in this bound. So we're wondering if we could do better. Could we get a sharper bound than just this obvious bound here? So we found there is a way of doing that. So this lemma is just summarizing what's on the previous slide essentially, but instead of bounding with this inequality, we're doing something a bit different. And we've got these alphas here, which look a bit strange at first sight. So what is alpha? Well, alpha p is the maximum of two things. It's a to the p to the 1 over p, and a to the p plus 1 to the 1 over p plus 1. So there's a couple of consecutive norms of powers there with appropriate roots. And so essentially what's going on is we've got something here that will give us a sharper bound than the one thing I just wrote on the left-hand board. So I need to motivate where that's come from and what the idea is. So let's do that on the next slide. So what we're trying to do is summarize at the top. We want to bound that power series. And we want to allow for, or take account of the possibility that A could be very non-normal. So what is a non-normal matrix? Well, strictly speaking, it's just a matrix that does not, so that AA star is not equal to A star A. Okay, because a normal matrix has an equal there. So one measure of non-normality would be to look at the norm of the difference. And I suppose you'd have to scale it for this to make sense. Maybe divide by norm A squared. And if that's much bigger than 1, you could say A is somehow very non-normal. So that would be one way of characterizing non-normality. Probably a better way of characterizing non-normality is to take the shear form. Q star AQ is T. Write that as diagonal plus strictly upper triangular. And if the norm of the n part is much bigger than norm A, then that's, to me, a slightly better way of thinking about non-normality. So you've got a big off-diagonal part of the shear form. That's how I normally think of non-normality. So what does that mean? It means that the norm of A is going to be much bigger than the spectral radius, than the largest eigenvalue. Because the diagonal of the triangular factor has got the eigenvalues here. So rho A is just the biggest diagonal element of A. Norm of A in the Frobenius norm would equal norm of n. No, it wouldn't. Oh, actually, D, not A, D. So the upper triangular part of this shear factor is big compared with the diagonal. That's what I'm trying to say. And so that corresponds to saying that it's essentially the same as saying that the norm of A is much bigger than the spectral radius. Now there are various relations between norms and spectral radii. In particular, if you look at this quantity here, take some positive integer power of A and take the pth root, it's easy to see that's bounded by norm of A, because the norm of A to the p is bounded by the norm of A to the power p, and then taking the pth root will give you A. But this is also bounded below by the spectral radius. So these quantities always lie between rho and norm A, and in fact the limit of this sequence is the spectral radius. So these numbers are tending towards the lower bound in this inequality. So what's the point of that observation? If you have a very non-normal matrix, this is much bigger than this, and these things are tending to this. So these things could be much smaller than norm A. So if you can bound your series in terms of these things for a few small values of p, you might get a much sharper bound. That's the idea. That's the idea that we used. Okay. So I'm not going to go into the details of exactly how you can bound the series using these quantities, because it involves a couple of lemmas that I don't want to go into, but it can be done. And remember on the previous slide we had that business about you've got two consecutive members of the sequence that define alpha. So it's a little bit fiddly, but you can nevertheless get a bound that involves these sorts of quantities. Let me give an example to see how beneficial that can potentially be. So at the top there I've got a 2 by 2 matrix that's quite non-normal. Eigenvalue is 0.9 and minus 0.5, but the norm of the matrix is about 500. So the powers of this matrix clearly must converge to 0, but initially, because of the 500, there's a potential for growth. But more importantly, if you just take the norm of A and use that as a bound, well, so the black curve is the norms of the powers of A in the 2 norm. So in fact, they gradually decay. The red line is what you get if you just take norm of A all to the power k. So that line is just 500 to the power k, essentially. So just taking the norm gives you a terrible bound. Okay. So this inequality, norm of A to the k, bounded by norm of A all to the k, is absolutely terrible in this example. So that's the red line. So can we do better? So the circles correspond to looking at A to the 5 to the 1 over 5 and then raising that to the k. And it can be shown that for k greater than 5, this is a bound. Okay, so what I'm saying is that for k greater than or equal to 5, the norm of A to the k, you can show is bounded by norm of A to the 5 to the 1 over 5 to the power k. And so that gives us this blue line with the circles, which is clearly much better than the red one. If instead I take a 10 instead of a 5, I get this line. So I'm getting much more like now the exact behaviour of the powers. And in fact, the higher the power you take here in this example, the better you do, because the magenta squares show that as this integer increases, we get smaller and smaller numbers. Okay, so there's the potential for much sharper bounds by using this idea. The only problem is that we don't want to compute A to the 5 and A to the 10. You know, remember my assumptions. The only assumption was I can do A times a vector. I don't want to be computing norms of powers of potentially large sparse matrices. So, but what we can do is do norm estimation. So rather like when I was talking about the Fresher derivative and using a power-like method, we can use a one norm power method to estimate these norms without actually forming explicitly the powers of the matrices. Again, all we need to do is matrix times vector products. So the key ideas here, the bounds, in the truncation bounds, we're using this idea of these roots of powers. We will then optimize the choice of the degree and the amount of scaling to achieve a given precision, or a given tolerance. There's another idea we can use, which is sometimes helpful, which is shifting. So I can write e to the, if I look at e to the a minus mu I, that's e to the a, e to the minus mu, because the arguments commute. So therefore e to the a is e to the mu, e to the a minus mu I. So I can do any shift I like on A, and then I can recover the exponential via just multiplying by the appropriate scalar. So what's a good choice of shift? Well, what I'd like to do is minimize the norm, because it's the norm being big that's going to be make this method expensive. So I can choose mu to try and minimize the norm of the shifted matrix. And if you take mu as the mean eigenvalue, the trace over n, I think that minimizes the Frobenius norm of the shifted matrix. So that's at zero cost I can get a potential reduction in the norm. Another thing I could do would be balancing. So for the eigenvalue problem, we often do an initial transformation d inverse AD with d diagonal, chosen to try and reduce the sizes of the rows and columns. This is a standard thing that's done automatically when you call the LEPAC QR algorithm. And so it tends to reduce the norm of the matrix. So here we could also balance if we wanted, as another way to try to get the norm of A smaller. And the final thing that we can do is when we evaluate this Taylor series, we're supposed to do m terms of the Taylor series, or go up to the mth power. We could stop early if we find that the series seems to be converging. So if we're sure that the series has converged to our given tolerance, we can just not bother with the rest of the series, and that will save some work. Okay, so putting all those things together gives you this algorithm. So here I've got my shift at the top in line 1. I apply the shift in line 2. I've got another function that I'm not showing that computes the parameters m and s, because I've skipped over how we do that. But that's just sort of lookup table, really. And then we've got our outer loop, which is taking these s steps. So the whole range from 0 to t has been split into s pieces. And here we're accumulating the terms of the Taylor series, and the factorials are appearing through the j there. And we've got a little convergence test here. This says if two successive terms in the Taylor series are small, then we'll quit. But I want to check two successive terms and not just rely on one term being small. So if they're small enough, we can terminate the loop early, and we finally rescale by what's mu here? What's eta rather? Oh, eta is that thing up there. Okay, so it's very very simple in outline. Very easy to code that. But what about the effects of rounding error? Because the derivation of this algorithm did bound the backward error, but that's all in exact arithmetic. So can I say anything about the behavior in floating point arithmetic? Well, how accurately can I expect to get the answer? That's the key question. Well, for this we need a condition number. So let's just recap what the problem is. So the problem is, given A and B, compute e to the AB. So the data is both A and B. So an appropriate condition number would look at the effect of small perturbations in A and B on this quantity. So I've not written on the slide, but so what I want to do is look at e to the A plus delta A, B plus delta B, minus e to the AB, norm of that, and I want the limit as epsilon goes to 0 of the supremum of all delta A bounded by epsilon norm A, and all delta B bounded by epsilon norm B, and with that over epsilon norm e to the AB, I think. So that would be an appropriate definition of condition number. It's the usual thing, you'd make small perturbations to the data and look at the relative change in the solution and take the limit as those small perturbations go to 0. So that, I think, is my kappa x of AB. Okay. So earlier in the week I was talking about the condition number of a matrix function. So this is a bit something of an extension of that, because I've got the B in here as well now. And turns out we can get a reasonably sharp bound for this quantity. We can't get an exact expression, but the bound is given at the top there. So it's given in terms of e to the A and B. And we've also got kappa x, which is the usual condition number of the exponential itself. So that's a bound on the condition number, and let's assume that's approximately equal. So that tells me that the best I can do is a relative error less than or equal to this condition number times the given tolerance. So that's what I would like to show that the algorithm can achieve. It can give a forward error bounded by that condition number times that tolerance. So to check whether it does, I need to do a bit of error analysis of the algorithm. Question?
Is the bound independent of whether delta A commutes with A?
Is the bound
Independent of whether delta A and delta B commute with A?
Yeah, there's no assumption about commutativity there. Yeah. Well, in fact, B is not even square. B is a tall, thin matrix, so there's no notion of commutativity anyway here. So, does the algorithm satisfy this error bound? Well, you can do some rounding error analysis to get the thing in the middle of the slide there. So the relative error can be shown to be bounded by the unit round off e to the norm A, norm B times norm of e to the AB. I think for u I should probably put the, no, okay, it is u, unit round off. So I want to compare that with the expression for kappa x b. So let's just write them down side by side and compare them. So I've actually got u, start at the left here, u e to the norm A, norm B, norm e to the AB, and I want that to be less than the sensitivity of the problem, which is norm of e to the A, norm B. I'm not going to bother writing down the which type of norm it is, e to the AB, and 1 plus kappa x. And I can put a u on the right hand side as well. I can just assume that I'm going for a tolerance of u, because the actual relative error is condition number times the tolerance. So the question is that inequality true? And we can cancel some things straight away. There's a, what have we got? We've got a b on both sides that can go. Oh, I wrote that down wrongly, didn't I? That was in the denominator. Yeah. So if that e to the AB is in the denominator, and that is there on both sides, so it can be cancelled. So this cancels as well. So that goes. Okay, and the u's go as well. So it ultimately boils down to that, whether that's true. So if we assume that A is normal, so if A is not normal, I can't really say very much. If A is normal, then kappa x is just norm A, so this becomes norm A in the 2 norm. And so the only way I can have instability is if e to the norm A is much bigger than norm of e to the A times 1 plus norm A. Okay. So that can happen, because, for example, what is the 2 norm of e to the A when A is normal? Well, for a normal matrix, the 2 norm is just the modulus of the biggest eigenvalue. So that's e to the, if I order the eigenvalues by real part, it's e to the largest real part of any eigenvalue. let's just think of A being Hermitian for simplicity. This would be the largest value of e to the lambda I over all eigenvalues. So that's going to be either no, it would just be to the lambda max in that case, wouldn't it? So if A is symmetric, all its eigenvalues are real, this will just be e to the largest eigenvalue. But e to the norm A norm A means taking the moduli of the eigenvalues. So this is either going to be given by the largest one or minus the smallest one. So if I have a large negative eigenvalue, that will contribute, or that will define the norm. So so this could be much bigger than that if I have if the moduli of the eigenvalues are dominated by large negative eigenvalues. So that's how, even for a Hermitian matrix, this could be much bigger than that, and so I could potentially get instability. Okay. But fortunately, that can't happen because, remember, we shifted A. So we actually work with A minus the shifted spectrum. Now that shift results in the spectrum being symmetric about the origin. So the eigenvalues after shifting, the extremal eigenvalues, are the same distance from the origin. So minus lambda min is equal to lambda max after my shifting operation. Therefore, this is actually equal to that. So I can just cross that out because it's the same as lambda max. So with the shifting actually guarantees that, at least for Hermitian A, this is going to be stable. So that's quite nice. So that's still only for Hermitian matrices, but at least for for an important class of matrices, I'm able to show that the effect of round off on the algorithm is not any worse than the condition of the problem would justify. Okay. So let's just compare back with the sixth dubious way with its degree for Taylor polynomial and using an ODE integrator. So I think what we've done here more fully exploits the linearity of the ODE. Moreover, this method is based on the backward error, whereas an ODE integrator is always going to be based on the local error in this integration, which is a kind of forward error. And it's much better to bound backward errors than forward errors, because the forward errors are affected by the conditioning of the problem. So our error control should be better than that of any ODE integrator. There's another aspect to this that's interesting, which is something called overscaling. So remember, what we're doing is we're dividing A by a power of 2 to the s, to get it close to norm 1, doing some work, and then we're scaling back. And the question is, what happens if you divide by too big a power of 2, a bigger power of 2 than really necessary? Well, it's well known that when computing the exponential of a matrix, that can lead to some loss of accuracy. And we can actually illustrate that even in the scalar case. So if you consider x is 9.9 times 10 to the minus 9, and this computation is done in IEEE double precision. So if we just compare the first order Taylor polynomial with no scaling at all, just approximate e to the x by 1 plus x, that's a pretty good approximation because x is so small. But if you do a little bit of scaling and squaring and divide x by 2 and then square back, in floating point you get an error 3 times bigger. And for this slightly smaller value of x, this is actually exact to machine precision, and again this has got a non-zero error. So even in the scalar case, we can see that going too far with the scaling can have a bad effect on the error. And the analysis we've done with the sharper bounds reduces the chance of overscaling compared with the previous analysis. So that's good. Let me show you the results of some experiments. So what we're doing here is ALG-AH is the method I've just been talking about. And I'm going to compare it with XV is the algorithm from that paper by Sidji that I mentioned the other day from 1998, a MATLAB code that's Krylov based. Phi-PM is a code by Neeson and Wright that accumulates linear combinations of phi functions. But it can certainly be used also just to get e to the a times a vector as a special case. That's in MATLAB. And this is a MATLAB implementation of a method by Nick Higham based on rational approximation. So in fact, this test problem is taken from the paper by Higham and Weidemann and Schmelzer. I think Molly's referred to this work in one of her lectures. So this is a 9,800 by 9,800 Laplacian matrix. There's how you get it in MATLAB, Gallery Poisson. And we're computing e to the alpha AB for a couple of values of alpha, and we've set the tolerance to be full precision here to see how much precision we can squeeze out of these methods. And I'm normalizing the speed, that's the actual wall clock time, relative to algorithm AH. So if this has got speed 1, that was 2.8 times slower, this is 3.8 times slower, but here this method was 10 times faster. So the speed, clearly, the relative speed depends on alpha. MV is the number of matrix vector products required. So that's the only thing that alg AH does. That's really all it ever does is matrix vector products. These other methods do some other things as well. And the errors, well, we don't know the exact solution, so I'm actually showing you the relative difference between what alg AH computed and what the other methods computed. And you notice we're losing a bit of accuracy here. So although this was 10 times faster, there's a little bit of instability creeping into that method based on the rational approximation. The second experiment is a rather nasty non-normal matrix from the gallery. This is tri-W is an upper triangular matrix with quite a big off-diagonal part. So it's 20 by 20, and the diagonal is 1 and the off-diagonal is 4.1. So this is non-normal. And what we've got is t here. We're trying to compute e to the at times a vector b. B is defined up there. And I'm just actually looking at the norms of the result. So I'm not plotting errors here. I'm just plotting the curve e to the tab, its norm. You might want to know how the solution behaves. Well, and the solution decays because there's a minus in front of the matrix there, so its eigenvalues are actually all -1. So eventually these powers will go to 0. And that's what we see when we use our method. But in fact, all the other methods leveled off around here. So they leveled off when the norm was about 1 due to some form of numerical instability. So this is a typical example of the hump phenomenon that's described very well in the 19 dubious ways paper, that when you have a non-normal matrix, even if eventually e to the a tends to 0 or e to the ta, there's often a hump initially. And the height of the hump is a measure of the non-normality. So that hump's about 10 to the 6 or 7. Okay. And the problem is when you have that hump, errors introduced at the top of the hump can then affect the later computations, which is I think what's happening in those other methods. And then the third experiment is with some couple of matrices from the Harwell-Boeing sparse matrix collection, and also the 2D Laplacian. And I've compared the algorithm with ODE15S. This is MATLAB's stiff integrator. And again, there's quite a variation as to which method is faster. ODE15S is pretty slow on the first couple of problems, but actually faster on the 4 times Poisson problem. But then if you look at the error, ODE15S got the wrong answer for the 4 Poisson problem. So I think this is a good example of this backward error-based approach is more reliable than an ODE integrator having to do its local error tolerances and control error in that way. So we were aiming for about 8 digits of accuracy in this test. So that shows a few different facets of this method. And I guess the key point from my point of view is it doesn't require any assumptions on A. You just give it A, give it the tolerance, and it's, it's competitive with these other methods. So let's just do a little comparison with Krylov methods. And first of all, just to recap once again, you've seen this a few times now. The idea of the Krylov method is to use this approximation where you generated Q and H from the Krylov process, H being upper Hessenberg. So here's a table, and we can debate whether the things need adding or subtracting from this table. But so the algorithm I've been talking about, if you look at the algorithm itself, clearly the dominant cost is matrix times vector. So if you profile the algorithm in MATLAB, indeed most of the time is spent in matrix vector products. Krylov methods have to do other things. They've got to build the Krylov recurrence, they've got to compute e to the h, and from my experience with the codes I've been using in these tests, those costs can be significant. So it's not just the matrix vector product that governs the runtime of a Krylov method. So our method is really a kind of direct method, really, in that once you've specified the tolerance, we know in advance how much work we're going to have to do. Tolerance implies a choice for S and M. We know how many steps to do. We know how far we're going to go with the Taylor polynomial at each step. So we know in advance exactly how much work at most we're going to have to do. With the Krylov method, it is an iterative method. It needs a stopping test. It seems to be a bit less predictable how long it will take or when it will converge. There's no parameters to estimate here, as I said. We're not making any assumptions. With the Krylov method, there is the question of the Krylov subspace size, how big you allow that to get. And of course, that will then affect the storage, because you've got to store the Krylov basis. Our approach, simple as it is, just requires a couple of vectors of storage. And the method automatically will give you these values e to the at at multiple equally spaced points on the interval 0 to t. I think with the Krylov method, once you've got the h, you could compute some of these intermediate values if you want. B can be a matrix with several columns. For a Krylov method, you would need a block version of Krylov to do several columns. So I suspect that the block Krylov methods are not quite as well developed as the basic Krylov methods. But the Achilles heel of our approach is that the cost will increase, roughly speaking, as norm A increases. So if you have a very large norm A, that's going to really hit our method, especially if A is normal. If A is non-normal, then a large norm A might be alleviated by this trick we have of using the powers of the matrix. But if A is, say, Hermitian, then that trick doesn't really do anything for us. So if norm A is large, we are going to need a lot of steps. And Matrices analysis, in certain cases, shows some kind of norm A dependence, but not quite as bad, more like the square root. Any comments? Please add or disagree. That's appropriate. If you know more about A, then obviously you can build that into your method. Yeah.
Just comparing the Krylov subspace method usually works with the right inside B, but your method is like independent of the B vector.
Correct. We're not really using any properties of the right-hand side. The Krylov method does, because it's building the Krylov subspace based on B. So that's a good point. As B varies, our method will always cost the same. Krylov method, its cost will vary with B, I presume. Yeah. So what's a good B then? What's a good B or a bad B for a Krylov method? Any other comments? Yeah.
Could you say a little more about how S and M are determined? Sort of said you didn't want
Yeah,
to talk about it, but is it quite complicated? Is it?
Okay, if we go back to the case where we've not got the b, we're just computing e to the a. So for any given s, I can say, well, just let me go back a bit. So if you imagine we've scaled the norm to some value theta, then we can say what is the smallest degree of the polynomial or the rational function or whatever, such that the error is bounded by our tolerance. Solving this problem means doing some computation with the symbolic and high precision arithmetic, as I mentioned. So we have to bound this series and find the smallest degree so that the tail of the series will be less than the tolerance. So for any given theta I might want to plug in here, I can answer the question how big m has to be. So I can build up a kind of table of values, and then I can bring in the cost of evaluating the polynomial or the rational for that value of theta. So with that information at hand, I can then work out what's the optimal, well, what's the minimal cost so that I can achieve the desired accuracy. One complication is that, at least in the rational case, the cost of evaluating the rational function is not, I guess in the Taylor series case it's pretty obvious, isn't it? You've just got, if you add another term to the Taylor series, that's another multiplication. With a rational function it's not quite so simple, because the p and the q you have on the top and bottom are highly structured. And in fact, for the exponential, it's the case that qm of x is pm of minus x. So you get the same coefficients on top and bottom with alternating sign. So when you want to evaluate r, you can evaluate p and q together in a clever way that saves some work. So the total cost as m varies is not just a monotonically increasing function of m. It levels off at some points. So you have to take all that into account as well. So in the case of e to the a, that's roughly speaking the sort of ideas that you use. In the case of e to the ab, it's a bit simpler. And in fact, mathematically, there's no limit on m. The optimal m would be infinity, it turns out. But that wouldn't make any sense numerically, because it would just be unstable. So we actually impose a limit on m, I think of about 30, and then choose s to go with that m. So it's a little bit different for the e to the ab case. So that's the kind of idea. And I should say also that this computation, the whole thing depends on that tolerance. So we've worked out what the parameters are for tolerance equal to 10 to the minus 16, 10 to the minus 8, 10 to the minus 4, and each of those requires quite a bit of computation. You don't actually get much of a benefit by asking for less than 16 digits with our method, interestingly. So if you only want single precision versus double, there is a saving in work, but it's not huge. So somehow the Taylor series, or the rational, in the rational case, the Pardy approximant, it needs quite a while to get going, and then once it's got going, it delivers high accuracy quite suddenly. But asking for low accuracy, somehow it's still got to go quite a long way to get that low accuracy. So that's another way in which this differs from the Krylov method, I guess. Yeah, Marlies?
Maybe a short comment to the storage. Just we have talked here about the Lanczos, the Arnoldi process only. Another option is to use the Lanczos process. You can use a non-symmetric Lanczos process. But then, so that goes with three-term recurrences, breakdowns. So you have a fixed amount of storage for this algorithm. But unfortunately, for building the approximation to a matrix function, you usually require the whole basis. But however, you could do a second run with just the right Lanczos vectors if you have stored this tridiagonal matrix, and then that costs you another m matrix vector product, but you can go along with a fixed storage. some additional cost. Does there's comments because
Yeah.
I've not talked about ventures algorithm at all.
Right.
And of course,
Okay.
ventures and other difficulties. Yeah. You don't have also normal basis and then arises other stability issues.
Yeah. So at the end of the section on software, I have got a section with a little case study in it. I'm not going to go through this. Just want to point out that it's there. And what it's about is taking the Bjork-Hamelling method for computing the square root and looking at how to implement it in a fast way on a modern architecture. Okay, so there's some ideas there of using blocking and some fairly simple ideas about blocking and recursion to produce a fast square root. And that is the work done as part of this project I mentioned and is the code that's going in the NAG library. So have a look at that to get some ideas on how to use blocking and recursion for faster execution. But I'm going to finish off now with this extra section which I've prepared. So some ideas about how to do research. What this is about really is just thinking, standing back a bit and thinking, what are the things we do that lead to interesting pieces of research, and trying to look at it from a bit of a meta level. So one thing that people sometimes do is think of a new metric for measuring the cost of a problem perhaps, or the accuracy, a new definition of cost or accuracy, or a new, depending on a new computer architecture, the thing we're trying to minimize may vary. Nowadays communication is there as much as the number of flops. So the metric that we're trying to minimize on certainly systems with huge numbers of processors in a distributed memory fashion wouldn't be just floating point operations, it would be that plus some measure of communication. And once you have this new metric, then what's the best algorithm may well be different. So you can develop a new metric and then develop a new algorithm that is best on that metric, or maybe tweak an existing algorithm for that metric. Okay, so that's one thing that quite a lot of that work stems from, this idea of changing the metrics. Sometimes you can spot assumptions that people have made that aren't really necessary. And a classic example is Strasson's method for fast matrix multiplication, published in 1968. So he showed that you can multiply two n by n matrices in order n to the log 2n, n to the log 27 operations. So that's n to the power 2.81, as opposed to n cubed, which is the usual cost if you do matrix multipliers rows times columns in the usual definition. So what you realize was you don't have to do an inner product of these rows and columns. You can get the elements in the product in a different way that reduces the number of operations asymptotically. So, thinking originally about the problem and finding some other way of attacking it. A lot of papers are about simpler proofs. So it's always good to have an easier proof of an existing result. So those very often are publishable, a nicer proof of something that's there already. Or you might be able to weaken the assumptions in an existing result, ideally getting the same result, or even if you end up with a weaker result, that will often still be of interest. So what are the really necessary assumptions that you have to make? The holy grail, in a sense, of numerical analysis is to develop algorithms that are both faster and more accurate. Usually there's a trade-off between speed and accuracy. But in quite a few cases, you can actually get greater speed and greater accuracy at the same time. The first examples I saw of that were probably from the work of Jim Demmel in the 1990s on some of the SVD work where this happens. So what can happen is that by making the algorithm faster, somehow it's doing fewer operations, there are fewer rounding errors, so intuitively it's not unreasonable to think that faster might mean more accurate. But usually the more accurate does not actually just follow from doing fewer operations. It's the type of operations that you do. And that they are less prone to giving errors in the result, or larger errors. So actually the e to the a scaling and squaring algorithm from 2005 is an example of this. So it was developed to be, really developed to optimize speed and accuracy together, and was able to do so in a way that made it faster and more accurate than the previous version. And then finally, developing algorithms that can solve problems that nobody can yet solve. So a good example, thinking back to the slides on Tuesday, was that example of the very large sparse covariance problem. They generate random vectors from a given distribution with a large sparse covariance where we couldn't Cholesky factorize C, so the standard techniques just wouldn't work, but by using C to the half, that approach will work because it just requires matrix vectors operations. So it's always good if you can find a problem that hasn't yet been solved and solve it. Or make up the problem that you then proceed to solve. But you have to convince people it's worth solving, I suppose. Okay. So those are some thoughts on the bigger picture of doing research. And I'd welcome any other ideas. I'm sure that's not a complete list of what would be a good thing to do if it would be to take an issue of, say, the latest SIAM Journal on Matrix Analysis and Applications, and then go through the papers and just classify them as to which of these bullets they fall into. Or if they don't fall into any of them, maybe we can have some more bullets. So have a table, different types of research, and then classify articles according to what they've actually done. If they've not done any of these things, then you might wonder whether the paper should have been published, actually. There must be something in the paper that's made it worth publishing. Who's heard of reproducible research? Okay, so quite a few people. Good. This is something that's been of growing interest in recent years. There's a Wikipedia page on it from which I've just taken these two statements. The definition being that it refers to the ability of an entire experiment or study to be reproduced, or by someone else working independently. So it's something that in the experimental sciences, I guess, has been around forever, the idea that you document your experiments in a way that other people can reproduce them. But in the world of numerical computation, we've traditionally been very bad at this. Even ourselves being able to reproduce an experiment we did 5 years ago is often impossible. And we can't even find the code that we ran. I think it first was talked about by the signal processing group at Stanford in the late 1980s. John Clare Boot and David Donahoe was also heavily involved at this time. So I think he proposed the term. And since then there's been a gradual increase in interest in this, so that nowadays this is quite a well-known term, and a lot of people are trying to do this to various extents. So I think to a large extent this term is meant to apply to experiments and computer programming, computer experiments, but it also does apply to writing papers. So I'm not going to talk too much about the experiment side. I just want to say a bit about how this applies to writing papers. So back in the 1980s, the way I worked was I would start, I'm ready to write a paper based on a piece of research, so I create a directory on my computer with a name describing the project, and I'd say edit paper.tech, and I start typing away, and I'd save it and run it through LaTeX and correct the errors and basically repeat for the next several weeks, saving and running and LaTeXing and printing and reading drafts and refining. And it's still called paper.tech after 6 weeks' time. So I've not kept any of the intermediate versions of the paper, unless I took a backup on my system, which I might do, say once a month, perhaps in those days. So I've lost all the intermediate information, which in retrospect is not a good idea, because there may have been bits of text or ideas that I put in a draft and then took out because I thought they were wrong. And later I realized actually, well, maybe they're not wrong. And maybe now if I were to look back at some of that work, there'll be things I'd tried and discarded that actually I now realise would be worth pursuing further. So that's I think not a good idea. I would perhaps call that irreproducible research in the sense that you're throwing away a lot of the intermediate information that could turn out to be valuable. So what I then eventually started doing was numbering my versions sequentially, paper1.tech, paper2.tech and so on. My record is getting up to about paper21.tech, but it all depends on how often you rename, of course. So how do you decide when to go from paper 1 to paper 2? I would probably tend to do it that paper 1 would be the first complete draft, which I would then print out and read. I'd make corrections and that would give me paper 2. I think that was roughly how I worked. So that's much better than the first approach. But it's pretty hard keeping these versions numbered and in the right place, and not overwriting them and remembering to rename. It's not an ideal way to work. And if I quickly go into the directory and try and find the latest version of the paper, I'm not instantly going to know which one it is. Or indeed, if I do a search in my in Spotlight on the Mac or Windows Search and it pulls up a phrase, it could be directing me to the wrong version, to an earlier version of the paper. So what I now do is I put my papers into a version control repository. So they're still just paper.tech, but frequently I'll commit it to this repository, so it gets saved into this database somewhere on the system, and any version that I've put in the repository can be got back later. Can be pulled out. And when you commit it to the repository, you make a few notes to say what has happened. Like I've added a new section 3 today, or whatever. So that is the way I work, and the way I think is probably the best way to work nowadays. And I think that's also good if you're collaborating with co-authors, because you can all be committing to this same repository, adding comments about what you've done, and having this central database of the different versions of the paper. So personally, I only use a repository on my own machine, so we've not got to the stage of collaborating through a repository, partly because we don't have easy access to one at Manchester at the moment. So what we currently do in our group at Manchester is use Dropbox. So we share different versions of the paper via Dropbox, but then perhaps locally each of us has our own separate repository. And that works pretty well. So have a think about that idea. And there was a very interesting workshop. I wasn't at it, but the website has many of the presentations. This was last December at the Institute for Computational and Experimental Research, SIAM for Methods, at Brown University. That workshop had many of the key people in the area there, and there are some very good slides that you can pull down and have a look at. So I strongly recommend having a look there to find out more about the state of the art in reproducible research. As to what I do, as to what particular repository I use Git, which is called a distributed control system. So that means that you have a complete copy of the repository on every machine rather than just one central one on some remote server. And there are lots of others, but Git and I guess most of them have got all sorts of interfaces. You can work from the command line. There are some applications that give you a WYSIWYG interface. You can do it from an editor. There's even a nice way you can get LaTeX to automatically print at the top of the page which version or date that document was last committed. So it's really quite a nice system to use. And with Git itself, there are various websites that will host repositories, and people use this as a way of sharing codes, in fact. So I guess Git was really designed for sharing for computer codes, but it works equally well for papers. I can just show you so this is the slides for the talk here. So if I go into here, this is what I would do if I wanted to commit the latest version. But there is the list of commits I've done, starting. It's a good job I didn't start writing these slides on the plane here, because that would have been totally visible, but thankfully it says I started 5 weeks ago. It looks a bit better. And there's a slightly more detailed version there. So this shows you well, there's only one file here, so it's a very simple setup. It tells you how many insertions and deletions were done each time. But I can go back to any of those earlier versions and pull them out and look at them again. So that's something I would recommend having a serious think about. Other tools, so have anybody heard of LaTeX diff? Does anybody use that? I only found out about it maybe a year ago. It seems to come with, it comes with TeX which is the distribution I use. It's available on the CTAN archives. It's a Perl script that you will take two TeX files, typically an old and new version of a paper, and it will produce a diff file, but the diff file is again a TeX file. And the diff, so if you know LaTeX paper diff TeX, everything that's been deleted from going to the old to the new will be highlighted with in red with a squiggle underneath, and everything that's new in paper new that wasn't in paper old will be in blue. And it's a great way of seeing the difference between two papers. So if your co-author has done a new version of the paper and you run the old and the new through LaTeX diff, it's the easiest way I know to see what changes have been made. So it's really very good. Sometimes the paper diff won't actually LaTeX itself because there's a lot of messing about with the LaTeX, but you just have to comment out a few lines and you can usually get it to run. So that's well worth trying as a way of quickly seeing the difference between two different versions of a TeX file.
I can say that a common error with diff is that it inserts a new line. You have to remove a new line. I found that's the most common.
It does what?
It gives you an extra new line.
Extra?
And it doesn't apply if you remove the new line. So it has a blank line that you remove.
Yeah, although a blank line is not really significant in LaTeX anyway, is it? It's not going to print. Yeah. Yeah, so it's not perfect, but it does a pretty good job. I've got more about some of these aspects on. We have a page for the group called a Need to Know page. So when you get the slides, if you click on that Need to Know, it'll take you to that page. So there's more information about all kinds of things like this there. Part of reproducible research nowadays is wrapped into this idea of literate programming that Donald Knuth promoted back in starting in the 1980s. So when Knuth wrote the TeX program, he actually embedded the documentation in the TeX. So he was writing in, I think it was in Pascal, but he was able to write the program that both produced the ultimate Pascal program and also produced a separate document that was the documentation for TeX. So he developed this idea of literate programming. It's not really caught on because it's pretty hard to do this. As I think Knuth himself said, you have to be not only a good programmer but a good writer for this to work. But in recent years, the idea seems to be becoming a bit more popular because there are systems now that make this a bit easier. And there's a great example in this paper in 2012 in the Journal of Statistical Software. So they show how using, I think this is using Emacs org mode, you can produce the paper, run the experiments. In this case they're using R for the stats experiments, generate the figures, and just everything is done by essentially one call from one piece of source code. So that's worth having a look at as an interesting example of combining literate programming with modern tools and giving you what's essentially reproducible research. What they've done works great if you've got fairly small computations. If you've got computations that take many minutes or a few hours, like some of us do, it's not quite so appropriate. I guess there what we'd have to do is make sure that we don't repeatedly do those computations, and I think that these ideas can be tweaked so that that's the case. And there's also, along the same lines, there was a SciPy meeting recently in Austin, I think it was in May, and there's a pretty good presentation there by a guy called John Kitchen, who's a chemical engineer, and he was illustrating how he does things in a similar way. So he has a couple of books online. One is a book about Python, about scientific computing with Python, and it's all produced in a very automated fashion from Emacs R mode, or org mode. So that half-hour presentation I also think is worth a look if you're interested in these ideas, because some good things that we could copy there. So a couple of weeks ago I was at the SIAM annual meeting in San Diego, and I organised with Tammy Calder a mini symposium about the professional use of social media. And there are four talks in the mini symposium which all are available from my blog post that I've linked to at the top. The most interesting for you is probably the one by Tammy Calder. She's some very good advice on how to make your publications available online. So there's many different ways to do this nowadays, and of course it's something you will want to do. Once you've written a paper, you want to make it available to people. We all want to get lots of citations and show the impact of our work. So there's some good ideas from Tammy on how to do that, including exporting from bib files automatically to HTML that you can then put on your web page. So you might want to have a look at Tammy's presentation. And she talks about Google Scholar, Microsoft Academics, search, and the pros and cons of many of these different online sites that will indicate citations to work. David Gleich gave a good survey of different social media tools as well that's worth looking at. I was talking about blogging and tweeting, and Karthika from SIAM was talking about more generally the importance of blogging for scientific communication, and making the point that there's not so much in the way of scientific journalism nowadays. The New York Times used to have a lot more in the way of articles about mathematics and mathematical topics. They have far less nowadays. So to some extent, blogging has replaced many of those articles as regards educating the general public about what's going on in mathematics. So there is an important role there to be played by bloggers. A couple of people have asked me about journal publication times. So I dug out some figures from the recent SIAM board meeting. So SIAM I know is very concerned about publication times, and it's been working for many years to try and reduce the time from submission to you first getting the referee reports and then ultimately a paper being published. So the current means over the last 5 years, from the time you submit to the time you get the referee reports, is 3.7 months for CISC and 3.4 months for CIMAX. So those are median times rather. So that's the sort of time on average you might expect to wait to get reports. The variance is pretty big though. You might get the reports in 6 weeks, you might get them sometimes in a year, unfortunately. So it does vary a lot. And what I would say is if you're at all concerned, don't feel at all bad about sending a message to SIAM. If you log onto the journal webpage, in the case of SIAM, there's a send manuscript correspondence box, and you can fill in the form and just say, do you have any news on the status of my paper? And what will happen then is that the editorial assistant will email the editor of the paper and ask them to report back on what the situation is. And the benefit of that is that if the editor has maybe temporarily forgotten about your paper, or he's been travelling and got a pile of things to get through, it might push it to the front of the queue a little bit more. So it can do no harm to politely ask for an update on the status of the paper if time has moved on. But you might as well wait until perhaps about the mean of 3 or 4 months before doing that. As I say, SIAM is working very hard to get these times down. Ultimately, it's down to the community and the referees. And ultimately, the reason things are slow is referees are, just taking a long time. So we can all set a good example. You can all set a good example by being efficient referees yourselves and help get these times down. Once a paper's accepted, there's then another delay while, of course, it's copy edited. You have to proofread it and send your proofs back, and then those changes are entered. So the total time from submission to to publication, so first of all, here's submission to acceptance. So for papers that ultimately get accepted, this is now average rather than median, so it's getting on for a year. Then from acceptance to publication online, will typically, I think, be about 2 months. Okay, so that will give you a feel for the overall, for the timescales. That's for SIAM. Other publishers could be different, and it does vary by area. So in some areas, even amongst SIAM journals, in some areas referees are slower than other areas. So it's largely the way the community is used to behaving, really. So in applied, in physics journals, chemistry journals, I guess things could often be a lot quicker. It does very much depend on the community. I just got an email this morning this is on the ILAS mailing list. So the announcement is now out of the next householder meeting next summer, and you can now apply to go to that. Who's heard of the householder meeting? Right, well, it's been going since the 1960s. It was called the Gatlinburg Symposium originally. The first one was held in Gatlinburg, Tennessee, in about 1961. It's every 3 years, and it's really the major international meeting on numerical linear algebra. I guess this and the SIAM meeting, the SIAM SIAM meeting. So it's a great meeting to go to. It tends to alternate between the US and Europe. Last time it was at Lake Tahoe. So in 2014 it's going to be in Belgium. It's a week-long meeting, usually held at a relatively remote location. It is limited in the number of people that can attend, because the remote location tends to mean a smaller hotel which has a limited capacity. So it's normally limited to around 125 to 140 people, depending on the size of the hotel. So attendance is by making an application and then being selected to attend. So that's what it says, by invitation only. And this email is soliciting applications by the end of October. So the application consists of a 2-page abstract, and if you're a new or recently finished PhD, a short CV and a letter of recommendation from somebody who might be your supervisor or might be somebody else. And it's not limited to more experienced researchers. There's always quite a few PhD students go to the householder meeting. So I'd recommend it. It's got very much the same feel as this summer school, in fact, because everybody has lunches and dinners together with randomised seating. I think that's where the randomised seating idea came from, the householder symposium. So I would encourage you to think about going and, submitting an application at the end of October. It is competitive, so to be selected you'll need to have a pretty good CV, an application, and given the limited number of attendees, not everybody here would be selected if you did all apply. But keep that in mind, because that will be a very, I think, enjoyable meeting next summer. So finally, I'll just switch to a few words on writing. So I'm just picking out a few slides here from a talk I've given before on how to write mathematics. Very brief, and there's a whole list of issues around writing a paper. There's a long list, and I'm just going to pick on a very, very few points that fall into that list, different points. So one of the, when I was writing my book about mathematical writing many years ago, I was reading what other people had written about scientific writing. And there's a nice book by Vernon Booth, and he had this chapter about grammar and so on. And he said, keep in mind TW Flying, and this was an acronym for those whose first language is not English. Okay, so he was saying to those of us who are native English speakers, keep in mind that the people reading your paper will not all be native English speakers, therefore don't be too florid and complicated in the way you phrase your sentences. Try and keep things simple, because it will be understood better by foreign readers. So I thought that was a very good comment, and I've always tried to bear that in mind. But then there's a converse to that, which I've invented. TW Fly, keep in mind those whose first language is English. So if you're a non-native writer and submitting a paper to a journal, it is going to be read by editors and referees who are native speakers and who do have a certain standard of writing that they expect. So do make sure that when you submit a paper, it has been carefully checked by a colleague, perhaps someone who's experienced in writing papers, because the worst thing you can do is send your paper in with howling grammatical errors all over the place. It'll most likely just be sent back, and you'll be told to, send it in again when you've revised the grammar. But you really want to get the grammar and the spelling correct. So that's just one little comment. As an editor, it is good if authors have taken a bit of time to have someone who's reasonably familiar with English to check these sorts of elementary things. I thought I'd say a few words about titles, because I'm always find that titles are, people don't spend very much time choosing a title. So if you flick through the title of the latest issue of SIMAX or CISC or SIAM or your favourite journal, there's not many titles really stand out. So what the title should do is summarise the content of the paper in a concise way, and if possible do so in a catchy way. 19 Dubious Ways, I keep saying, is a great title. So Kelly, who was a topologist at Berkeley, has this great example that Paul Halmos mentioned of someone had a title of a paper, a decomposition of compact continua and related results on fixed sets under continuous mappings. And Kelly said to him, don't put the whole paper in the title. So he then shortened it to simple links and fixed sets. So a title shouldn't be too long, but it does of course have to give some indication of what's in the paper. So here are some good titles I've seen over the years. I quite like how and how not titles, because it tends to make you want to read the paper. Algol 68 with fewer tiers was written by a guy in computer science in Manchester in about 1971. That paper is a syntactically valid Algol program. So as well as having a good title, there's something interesting about the paper, that it was a complete Algol program. If you have a nice crisp result in the paper, then the title can just state the result in some cases, and that's great. But it's not so common that we can do that. This was a technical report by Velvel Kahan from Berkeley, which I really like that title with the double meaning. Can you rely on your calculator? Can you actually calculate on a calculator? And this is called titular colonicity. It means you've got a colon in the title. They use colons a lot in the social sciences, but we seem to be rather afraid of them in mathematics. But there's no harm in using a colon occasionally in that way. Not so good titles, well, many titles that I see are just too general. So if you title your paper Perturbation Bounds for the Non-Symmetric Eigenvalue Problem, then there's already been 900 papers on that published previously. So what's different about this one? We can't tell from the title. So the title needs to say something about what's new in this piece of work. And a lesson I learnt many years ago, I gave a talk in about 1988, and the title was something like Stability of Fast Matrix Multiplication Using BLAS 3. And someone later said to me, I didn't go to your talk because I didn't know what BLAS 3 was. And I thought, oh yeah, I shouldn't have put BLAS 3 in the title, because there were some people in the potential audience who were not numerical analysts and not familiar with the BLAS. So don't put acronyms in the title if you can avoid it. So boundary value problem, boundary integral equation, some people will know what both those mean, some people will know only one of them, but here it would probably be better to spell them out. So ever since then I've avoided acronyms in my titles. There are some really bizarre titles out there in the literature. Look at this one, leg movements of stick insects walking with 5 legs on a tread wheel with 1 leg on a motor-driven belt. I can't quite decide if that violates my principles of titles, but what's actually happening is so horrendous, I don't even think about it. Or this one. I don't know whether this was an option for Princess Catherine, but nitroglycerine. what's going on there. So there are some really weird titles, and it's quite fun to search these out, actually. If you look at the Journal of Irreproducible Research, they often publish these sorts of discoveries. And then of course there's the glossary of these phrases that you're probably getting to know now in academia. So when someone writes it's well known that, it means they couldn't be bothered to look up the reference. It's generally believed that. A couple of other guys think so too. Of the correct order of magnitude. Well, it's wrong, so that all I can say is it's the correct order of magnitude. And we're really excited by this result. We might get a paper out of it. The most reliable figures are those of Jones. He was a student of mine, so it must be correct. Okay, so let me just have one slide about results, because in my experience as editor and referee, one of the most problematic parts of papers tends to be the results section, the experiment section. Not the actual maths, but when people try out something and then report on the experiments. So one common problem, I mean incredibly common, is just not to say the full environment you used. You know, what precision were you using? If you're using MATLAB, what version of MATLAB were you using? How were the random numbers generated? Were they random normal? Were they random uniform? What compiler options were you using? All these things, of course, fit into the idea of reproducible research, but people just frequently forget to say these things. So without that information, nobody can reproduce the experiments. Another common problem, and I just had to deal with this last week in a paper I was editing. So someone had added a new table to a paper, and they were giving errors to about 15 significant figures. So, you know, 7.5965135 times 10 to the minus 7. Well, most of those figures are irrelevant. All I need to know is 7 times 10 to the minus 7. The order of magnitude for an error is pretty much all you need to know. So you need to always ask yourself how many digits are really needed, and often it'll be fewer than you might be inclined to include. And it's very tempting when you're summarizing the results of experiments to extrapolate from the results. You know, so if I was on the paper on my e to the AB method, or I've shown it works quite well on 3 problems, so all I can say is it works quite well on 3 problems. I can't say this method works well in general. I can only say what I found on my particular experiments. It's very easy to go too far in drawing conclusions. And of course, we don't want to speculate, we just want to make objective statements about the effects of about the results of experiments. So do have a think about the way you present the experiments, because as I say, it's generally done not so well. To make things reproducible, we need to give all these details. Just to finish off, words about the sort of final stages of the process of production. Proofreading. So when you eventually get that paper submitted and it's been typeset and you get the proofs back, what do you then do? I think most of these comments here apply, let's jump ahead, they apply to when you're writing the paper. But when you get the paper back, there's a whole load of things you need to think about. Now nowadays, we tend to send in tech, and you would tend to assume that the tech you send in is the tech that was used. So you might be thinking that anything that you did correctly will still be correct in the final proofs. Unfortunately, that's not the case. Anything can happen. It has been known for papers to be retypeset completely, even though you've sent in the tech, because it was cheaper to have someone in India retype the paper than to send it from one office to another. That has certainly happened. So when you get the proofs, you mustn't assume that they're going to be correct. You must assume that they're going to be wrong and actually verify that they're correct. And there's a whole load of things to check for here, including subtle things like the O versus 0, L versus 1, whole chunks of text having been deleted by mistake by the person who was editing the paper. and so on. So what I tend to do is, I think the ideal way to do it is to read once through comparing the proof with the original version that you sent in, and then do a second pass just looking at the proof itself and not comparing that with the original. But you do need multiple passes to detect the errors. So I thought I'd give you a few tests to see how good you are at finding errors. So can you find the error in this sentence taken from a real published paper? Have you spotted the error?
Best unknown.
Yes, it should be best known methods. This is one of the first sentences in the paper. So that's got by all the copy editors. What about the second one? This is from an OUP book. So it'd be hard to overestimate. This is an incredibly common error. And I came across it just recently somewhere, I can't quite remember where. But this was an Oxford University Press book that had been copy edited, by a professional copy editor. Oh yes, this was a talk at the SIAM annual meeting last week from a lady from Ford Motor Company. She had played a couple of videos of one of the vice presidents of Ford talking about the company, and he made this error. He said something like, it would be hard to underestimate the importance of the computing group at Ford to our company. So we actually got it, and he got it wrong. She hadn't noticed the error and broadcast it to 1,000 people. So people just don't spot these sorts of errors. How about this one? This was, again, a real example. Yes, Ockenden, he wasn't so anonymous after all then. And then this one. Is there anything wrong with the second bullet there? Pardon? No. Pardon? Yeah, it should be 10 to the power 18. And this was from a proceedings where all the superscripts and subscripts had somehow got lost. So all numbers were just written out as the string of digits with no subscript or superscript, which is rather unfortunate for a book about physics, because there are quite a lot of sentences like this that then became rather silly. Manchester United. This is something I got through the door, I think, about an event that they were organising. That's Ruud van Nistelrooy, who used to play for Manchester United. Any errors? Yeah. Your should be Y-O-U apostrophe R-E for you are. What about this one? This is my brother's book. Is there anything wrong there? Well, look at the title of the book, Financial Option Valuation, and then underneath it says Principles of Laser Operation and Design. So CUP had put the wrong bit of text by the wrong book. From a newspaper. Okay, think of the double meaning there. That's just a very unclear sentence. They are so tiny. Does that refer to the hearing aids or the people? Another newspaper extract. This is the world's most common spelling error at the moment. Loose. Should be lose with one O. That's an incredibly common error. It seems to become more common in the last 10 years. I don't know why. Oh, I'll skip over that one because that's not something I've discussed. But this is the calculus textbook advert. Algebra and calculus, a problem for your student, apostrophe S. No, we don't need the apostrophe, thank you. A local Manchester newspaper. We've got some very terrifying pensioners in Manchester. And this is my local newspaper. What's wrong with that? Flies. That's not how you spell flies. F-L-I-E-S. So if you're going to make a spelling error, don't make it on the headline on page 1. That's my message to newspaper editors. You've probably seen this classic one before as well, from an early version of the Bible. Yeah. They're not, there's unfortunately been omitted from this one. Yeah, that's a well-known example. Even SIAM, unfortunately, is not immune to these sorts of errors. So in an article in Inside SIAM, you had the confusing suggestion that journal authors make their titles interesting but misleading, rather than interesting but not misleading. Okay. So yeah, everybody can make mistakes. So never assume that you've. Always do an extra pass as an extra check, would be my advice. And that's just my favourite cartoon. We shouldn't use contractions in our writing. I think you have to be a native English speaker to understand that one. So there's a lot more about that in my book on writing, which you can get if you're at you can probably download as PDF if you're at an institution that subscribes to the SIAM ebook scheme. So that's the end of my bit. So I'd just like to make a few final remarks. First of all, I think the organisation this week has been really superb, and we should thank everyone who's been involved locally, both students and faculty, in organising it. So let's give them a big round of applause. But in particular, I think Wego Geo, Zhajun Bai, Yang Feng Su have done a huge amount of work, and will be continuing to do so over the next week. So let's give them in particular a big round of applause. So it's been a big privilege to lecture here, and I know Marlies feels the same way. And there's been, I think, a very special atmosphere, which is really great. It's been good to see everybody working together and talking to each other, and I think that's really what these summer schools are about. And very much in the kind of event that Jingola would have liked to organise himself, and very much in a good honour to his memory. And I noted recently that of the postdocs we have at Manchester, 4 of them were at the previous Jingola summer school. So I think you probably are very much going to be the leaders of the field in the future. So I hope when I'm old and doddery, you'll remember that I once gave you a lecture. So I think you're in good hands for the next week with Peter Benner, Renkang Lee and Sherry Lee. 3 very experienced lecturers with talking about different aspects of numerical linear algebra. Li Jing is still around next week, so if you have any questions about my part of the course or the exercises, she's available to talk about them. I'm also very happy if you were to email me as well at any point after this week. I'll be happy to respond and help in any way I can. And I guess finally, just to remind you, make sure you join SIAM as a free student member, think about setting up a SIAM chapter locally, and consider applying for the Householder Symposium next year. So that's it from me. Thank you.